This is video number 10 of Thermodynamics 2. In the last video, we had already discussed the basic theory of axial flow reaction turbines and its velocity triangles and the term degree of reaction. We have derived equations for calculating power output and efficiency of 50% or Parsons reaction turbine. Now I will solve a numerical problem of reaction turbine. So let's read the statement. Stage of a steam turbine with Parson blading. So Parson blading here means 50% reaction turbine. Delivers dry saturated steam at 2.7 bars. So here the pressure at inlet of the at the inlet of moving blades is 2.7 bar, because Parson blading delivers dry saturated steam at 2.7 bar from the fixed blades, and fixed blades are actually the nozzles or the row of nozzles. So steam is leaving these fixed blades at a pressure of 2.7 bar, right? So this is the pressure at the exit of nozzle or at the inlet of moving blades at 90 meters per second. So this 90 meter per second is actually CAI. The mean blade height is 40 mm. So mean blade height means H blade height, and blade height we have already learned it is increasing in the direction of steam flow. So here we are discussing only a single stage. A stage means here single stage, and single stage means one row of fixed blades and one row of moving blades. So one row of fixed and one row of moving blades makes one stage of a steam turbine. Okay. The mean blade height is 40 mm. So the blade height is higher at the exit and lower at the inlet. So maybe I can show it here. For example, this is fixed blade, or the nozzle, and next is moving blade, and blade height is increasing in the direction of steam flow. This is moving. So this makes one stage. This fixed blade are attached to the casing, and moving blade is attached to the shaft. And blade height is increasing in the direction of flow. So here you have a lower blade height, and here at the exit of moving blade height is a little larger. So the mean blade height means this height is given, right? This height. This HM. Right. So this mean blade height is 40 mm, and the moving blade exit angle of moving blade, so that will be beta E, right? Moving blade exit angle is 20 degree, that is beta I. So this is actually beta E, not beta I, because moving blade exit angle is 20 degree. So let me correct it here. This angle is beta E, which is equal to alpha I. We have already studied in the theory. Okay, right. So this is beta E, which is equal to alpha I for 50% reaction turbine. Okay. The axial velocity of the steam is 3/4 of the blade velocity at the mean radius. So the axial velocity of the steam, which is represented by CF, and that is 3/4 of blade velocity. It means CF is equal to 3/4 of CB. Steam is supplied to the stage at a rate of 9,000 kilograms per hour. So the steam which is flowing through this fixed and moving blades, its mass flow rate is 9,000 kilograms per hour. So means m dot is given. The effect of the blade tip thickness on the annulus area can be neglected. So the blade tip thickness is negligible. If we see, if I draw the same diagram from side, so it would be like this. This is the wheel, this is shaft, and above this wheel these are the blades attached. Right. So here this is the moving blade. Right. So this is the edge of the blades, or top edge of the blade. I can draw this imaginary circle through which steam is moving. So this is shaft. At the center you have shaft. So here is the shaft, that is the wheel, and above this wheel these are the blades attached. So steam is flowing axially, means into this slide or into the screen. Right. So this area, this whole area, is the annular area in the form of a ring through which steam is flowing in the axial direction, means into this screen or out of the screen. So here what is given, the blade tip thickness. This blade tip thickness is negligible. So that's why you can say that this is the area through which steam is flowing when you neglect the blade thickness. If thickness is not negligible, then you have to subtract the thickness area from this annular area through which steam is flowing. Right. So the effect of this blade thickness, tip thickness, on the annulus area can be neglected. So this is the given data based on which we need to now determine the rotational speed of the wheel, means n, with which it is rotating, the diagram power, the diagram efficiency, and the last part is to find out the enthalpy drop of the steam in this stage. Stage here again means both fixed and moving blades. One row of fixed and one row of moving blades makes one stage of a reaction turbine. Okay, so let me erase all this. So now we'll solve the problem, part 1. This was the given data. Pressure at the inlet of moving blades, CAI, mean blade height, exit angle of moving blade, which is equal to inlet angle of absolute velocity, alpha I, for 50% reaction turbine. CF is equal to 3/4 of CB. Flow velocity is 3/4 of blade velocity. This is the total m dot. Mass flow rate, blade thickness is negligible. Now part 1 is to find out the rotational speed, and we know the formula from where we can find out the rotational speed, and that is given by 2 pi Rn is equal to Cb, or you may also write it in the form of diameter. Then it will be pi dn is equal to Cb. So this is the equation from where we can find out the revolutions per minute or the rotational speed of the wheel. Now in this equation, CB is not given, and also this R, mean radius of the wheel, is also not given. So there are three unknowns but only one equation, so we need to determine first this R and CB so that we can find out then the revolutions per minute or rotational speed of the wheel. So now we have to see how we can find out this R and CB. So CB is here from the given data is linked with CF, right? So CB is linked to CF, and for CF, what is given, CF is equal to 3 by 4 of CB, right? Now, what is CF? Flow velocity, and we know from velocity diagram that CF is equal to CAI sine alpha I. So if we see velocity triangle, so here is the velocity triangle, and from this triangle we know this this dB represents flow velocity, and that is equal to CAI sine alpha I, right? And for 50% reaction turbine, CFI means dB is equal to CFE, which is EC, right? So there is no change in flow velocity for 50% reaction turbine. So it means we can find out CF from velocity triangle, and that is CAI sine alpha I. So now CAI is given, alpha I is also given, which is 20 degree. So just put values and we can find out CF. So now CF is calculated. CB is 4 by 3 of CF. So CB is equal to 4 by 3 of CF. So CB is 41.04 meters per second. Right. So now CB is calculated. Now in this equation we have now calculated CB. The next important parameter which needs to be determined is R. What is R? R is the mean radius of the wheel, and this radius is linked to the fluid flow annular area, which we just drawn. So the annular area through which the fluid is flowing, and this annular area can be linked with mean radius R. So we will try to find this R from this area, and this area, this annular area through which fluid is flowing, and which fluid is flowing, this one, 9,000 kilograms per hour. It means we can link this annular area with mass flow of 9,000. So area is linked to mass flow rate, and we know the equation of mass flow rate, m dot is equal to rho AV, where rho is 1 over V, or specific volume. A is the annular area through which fluid is flowing, multiplied by velocity, which is perpendicular to this area, and we know this velocity which is perpendicular to this area is CF, flow velocity. Right, so this is the area through which fluid is flowing multiplied by the flow velocity, which is CF, divided by V. So this is the formula from where we can find out area A, and then with the help of this area A, we can find out the radius or mean radius of the wheel. So here, what is V? Steam which is entering into the moving blade. It is dry saturated. Here it is written what is, and dry saturated doesn't mean superheated. Dry saturated means it is saturated, and dry means x is equal to exactly 1. Right, so we can find out at this pressure 2.7 bar specific volume from saturated steam table. So from saturated steam table, dry saturated means V is equal to Vg at 2.7 bars. So from the steam table, this is the value. right? 0.6686 meter cubes per kilogram. So in these steam tables, all these values are given for 1 kilogram of fluid or steam, right? So now in this equation, m dot is known, 9,000 kilograms per hour. Cf is already calculated, which was 30.78 meters per second. Now V is also known from saturated steam table. So from this equation we can calculate area. Area is only the unknown in this equation. So from here we can find out the area, which comes out to be 0.054 meter square. Right. You have to be careful about the units. This is in meters per second, CF, and this is kilograms per hour, so it has to be converted into kilograms per second also, so it has to be divided by 3600, so you have to be careful about it. So let me write it here. 3600, it has been divided with 3600. This 9,000 has to be divided with 3600. So then you will get this answer. Area is equal to 0.054 meters square. So now this annular area is now known, right? So A is the annular area of flow. And what is this annular area? That is 2 pi RH. Now let's clarify this thing. So I have made another slide to clearly show the annular area. So here you see the turbine wheel. That is the wheel over which these blades are attached over the whole periphery. Blade thickness is negligible, so this is the annular area through which steam is flowing, right? So this is the height of the blade, this portion, right? And this, from the center of this rotor to the tip of this blade, this represents the outer radius of this wheel. Similarly, this at the bottom of this, from the center of this wheel to the inner edge or the bottom edge of this blade, this is inner radius of the wheel. And now we can also show the mean diameter or mean radius, and that is given by this R. So this dotted line is actually passing through the middle of this blade. So that R represents the mean radius of the wheel. So now from this diagram we can write the annular area. This is the area through which steam is flowing, this whole area. Right. And this area is given by 2 pi r, the circumference, 2 pi r, mean with respect to mean radius, multiplied by the height of the blade, which is h. Right. We can also write the same area as pi into r naught square minus ri square. So this area and this area are exactly same. Both represents the annular area of flow. Okay. Now we can further write this equation in terms of height, because this height, total height, can be divided into two parts, h by 2 and h by 2. If this is the mean radius, so the height is actually h by 2, h by 2 with respect to this dotted circle. So now we can write the same equation in terms of h and r, mean radius, right? So the same area can be written like this: r naught is equal to r plus h by 2. R naught can be replaced as r plus h by 2. Similarly, Ri can be written as R minus h by 2, right? So this is the same angular area of the flow, which was given as 2 pi RH, and the same area can be written in terms of R naught and Ri, and the same area can be written in terms of mean radius R and height of the blade. So now we'll use this formula to find out this R, because we need this R to find out the revolutions per minute. So let's go back. So this was the angular area, which can be written in this form, and then this can be written in this form. We have seen now in the figure also. So now just put values, because area was already calculated from this formula, right? And this was 0.054. So this area is equal to this term. In this term, the only unknown is R. Height of the blade is given, which is 40 mm. So 40 divided by 1000 to convert it into meters, right? Because area was in meter square. So this equation is clear. So in this equation, the only unknown is R, and we need R here in equation 1. So from here, we will calculate R. It comes out to be 0.215 meters. So now R is known, area is known, R is known, CB is calculated. So now from equation 1, CB and R is calculated. Now the unknown N, which is the part 1, to find out the rotational speed of the wheel, can be calculated. So just put the values of R and CB, so N comes out to be 30.4 RPM. So this was part 1, right? Now let's go to the next part. Next part is to find out the diagram power. So now we'll find out the diagram power. The velocity diagram. From velocity diagram, we know what is power output of Parsons turbine, and the formula is P is equal to m dot into CB into delta CW. Right, CB is already calculated in part 1. Now we need to calculate delta CW. To calculate delta CW, there are two possibilities. One is to draw the velocity triangle on scale and find out this length ED, that is delta CW, change in velocity of work. Or the other method would be to use the equation which we derived for reaction turbine, delta CW for 50% reaction turbine, that was 2CAI cos alpha I minus CB. So this will be more accurate. If you draw it on the scale, there will be some error, so value will not be exactly same as this one, 128.1. So it's better to use equation than graphical method, because graphical method will give some error. And so either use graphical method or equation will give you more accurate results. So I would prefer to use equation, so you can easily remember this equation for 50% reaction turbine. If not, then you can derive it. We have already discussed how to derive this delta CW for 50% reaction turbine. So anyways, for power calculation, we needed CB and delta CW. CB is already calculated. Delta CW comes out to be 128.1 meter per second. So now just simply put the values. M dot is 9000, CB was 41.04, delta CW is 128.1 divided by 3600, because 9000 is in kilograms per hour. This is meters per second, so that's why you have to convert it in meter per second, kilograms per second. That's why divided by 3600. Then if you want to represent the final value in terms of kilowatts, so you have divided this with 1000 also. So if you do not divide with 1000, the answer will be in watts. So now the final power or diagram power comes up with 13.14 kilowatts. Right, so it's not a very high power turbine because CAI is not very high. It's only 90 meters per second. That's why power output is also quite small. Okay. So now power output is calculated. Now will be part 3. Part 3 will be to find out the efficiency. For efficiency, we need to know what is power output, which we have already calculated, and then we also need to know what is power input. So output power divided by input power will give the diagram efficiency. So output power is already calculated, but you can calculate power output per unit mass flow rate. So then it is only CB into delta CW, just put the value, so then it is per unit mass, kilojoules per kilogram. If this is the power output per unit mass flow rate. Power input, we have also derived this equation. Let me show you again. This was the power input. We have discussed in the theory that power input is not just CAI square by 2 as it was in impulse turbine. In case of reaction turbine, it is CAI square by 2 coming from nozzle plus the velocity rise in the moving plates, which was CRE square minus CRI square divided by 2. Now we can, for 50% reaction turbine, we also know CRE is equal to CAI. So here you can replace CRI with CAI. So energy input is CAI square minus CRI square by 2. By putting CRE is equal to CAI in this equation. So this is the energy input. Okay, let's go back. So now we know the power input is given by this. Here it is not multiplied with m dot. So it means here it is the power input per unit mass flow rate. Because m dot is same. Right? Okay. So just put value. CAI is given, but CRI, we can calculate CRI from velocity triangle OAB by applying the cosine law to find out the CRI for a known CAI and for a known alpha I. So this is the cosine law to find out the CRI. CAI is known, CB is known, alpha I is known. Just put values and find out CRI. CRI comes out to be 53.32 meters per second. So now put the values in equation 4, CAI, CRI. So we'll get the answer in kilojoules per kilogram. That should be clear. There is no m dot. It is not multiplied with m dot. If you multiply with m dot, the same m dot, 9,000 kilograms per hour, we can also find out the power input in terms of kilowatts. So then we can find out efficiency. This is the output power divided by input power. But this here no m dot, so that's why the answer is in kilojoules per kilogram. That's why we have also written the output power in terms of kilojoules per kilogram. Right, so output divided by input, and input should be greater than the output, right? So that is the efficiency diagram efficiency of this 50% reaction turbine, and that comes out to be 78.7%. So this was part 3. Okay. Now the part 4 is to find out the enthalpy drop of the steam in this stage. Stage means not just the moving plate. Stage means both fixed plates and moving plates. In the whole stage, what is the enthalpy drop? Right. So once again, you should remember that stage means a row of fixed plates and a row of moving plates. So it's a 50% reaction turbine, and the enthalpy drop in the moving and fixed blades are same, because the total enthalpy drop is divided into two parts or equally. So moving and fixed blades are also termed as rotor and stator. So now we need to calculate the enthalpy drop in the whole stage, but we can first calculate the enthalpy drop only in the moving blades. And for the moving blades, how we can calculate the enthalpy drop? Okay. So here is the nozzle or fixed blades or stator. Next is the moving blade. So here you can see I'm showing it in increasing height, because in case of reaction turbine, pressure is dropping. When pressure is dropping means volume is increasing. So in the volume flow rate, you have to increase the height. Because volume is increasing, so you have to increase the area so that steam can occupy the more volume. More volume of the steam can be occupied in larger space. Okay, so enthalpy drop only in the moving blades. Now in the moving blades, the enthalpy drop is due to pressure drop, and this enthalpy drop is actually converted into velocity rise. So enthalpy drop in the moving blade will give rise to this rise in CRE, but this rise from CRI to CRE. So enthalpy drop in the moving blade is responsible for the increase in velocity, in the relative velocity. So that's why the increase in kinetic energy in the moving blades is due to this enthalpy drop, and that is given by CRE square minus CRI square by 2. So that is the enthalpy drop only in the moving blades, right? And for 50% reaction turbine, CRE is exactly equal to CAI. All right, and this we have discussed in theory. So CRE is equal to CAI, which is known. CRI was calculated in part 3. So just put values: 90 meter per second whole square minus 53.32 meter per second square. So this is kinetic energy, no m dot, so it means this represents the energy per unit mass. So the answer is 2.63 kilojoules per kilogram. That is the enthalpy drop in the moving blades. Enthalpy drop in the moving blades is actually responsible for this increase in velocity. So now it's a 50% reaction turbine, so the enthalpy drop in moving and fixed blades are exactly same. So we have calculated enthalpy drop only in the moving blades. So the total enthalpy drop in both fixed and moving blades will be 2 times of this one. So the total enthalpy, because we need to find out the enthalpy drop of the steam in the stage, not just in the moving blades, but now we have calculated for the moving blades. So multiplied by 2 will be the enthalpy drop of the whole stage. So the total enthalpy drop will be simply 2 multiplied by 2.63. So that comes out to be 5.26 kilojoules per kilogram. The next topic is optimum operating conditions for the blade velocity diagrams. So just like in impulse turbine, we found out the optimum condition of CB over CAI, blade to speed ratio, for maximum diagram efficiency. Similarly, we shall now also derive the optimum condition of the same CB over CAI for 50% reaction turbine. So the same procedure will be adopted here, that is to differentiate this equation which we have already derived for diagram efficiency for the 50% reaction turbine, and that was given by this equation 2.17. So here we can see this diagram efficiency is mainly a function of two factors. One is this ratio CB over CAI, second is cos alpha I. So alpha I we have already discussed, it cannot be zero, it cannot be too high, so this is normally a fixed parameter. So now the efficiency is mainly dependent upon this factor CB over CAI. So the same procedure will be adopted here, that is to differentiate this equation 2.17 with respect to CB over CAI and put it equal to 0. So now in this way we will get a point on the efficiency versus this CB over CAI curve. So let me show it again. So if we draw a curve between diagram efficiency versus this ratio CB over CAI, starting from 0, right? So we'll get similar curve like this one. And we are interested to know what is this point at which efficiency is maximum, right? So we are interested in this point, which will give maximum diagram efficiency, right? So what is this point? At this point, the slope of this efficiency curve with respect to CB over CAI is 0. Sorry. Yeah. So at this point, the slope is 0, means differential of this efficiency divided by the differential of the CB over CAI is equal to 0. So the value of blade speed ratio and power for maximum diagram efficiency, we can find out this value by differentiating this equation with respect to CB over CAI and put it equal to 0. It will be this point, right? So same procedure as was used in impulse turbine. Okay. So now after differentiating this equation, this will be the final answer. So the differentiation step, I have made a separate slide for it. So here you can differentiate the same equation. So in this equation, what we have done, we have replaced CB over CAI with X, right, everywhere, and alpha I is a constant here for a fixed or non-alpha I. So we want to differentiate this equation. So here you will apply the division rule of differentiation, right? So you can further simplify it by multiplying 2x into the parentheses. Right? So now you will differentiate this equation by applying the division rule. So division rule is clear, hopefully. So this comes as it is. Now the differential of this term is this one minus, so this term as it is, into differential of this term, okay, divided by the denominator square, right? So I hope this is clear. Now you can further simplify this equation. This term denominator will go on the other side, on the right hand side, and it will become 0. So now you will simplify this equation by multiplying these two terms and by multiplying these two terms. So this will be the final equation. Now in this equation, you will see a number of terms will cancel with each other. For example, this term will cancel with this term. Similarly, this term will cancel with this term, and so on. So finally, you get this simple form of the equation. So this will give you x is equal to simply cos alpha I, and x was CB over CAI. So this is the optimum condition, that CB over CAI is equal to cos alpha I. Okay, so there could be some typing error, so resolve it at your end. There is no need to panic at all. It's simple derivation which you have been learning since your FSC. So this is the, after differentiation, this is the optimum condition. So let's go back. So this is CB over CAI. It is the point on which efficiency versus CB over CAI curve, at which the efficiency will be maximum, right? And this CB over CAI should be equal to cos alpha I for 50% reaction turbine. So if you compare this equation 2.18, so you can see here for alpha is equal to 0, or then optimum for this reaction turbine means CB over CAI is equal to 1 if alpha is equal to 0. But for the case of impulse turbine, if you remember, this optimum was CB over CAI is equal to cos alpha I by 2, right? So in case of impulse turbine, it was 0, it was 0.5 if alpha I is equal to 0. So it means for the same CAI, CB, the blade speed of reaction turbine will be higher than for impulse turbine, right? Because in case of impulse turbine, this CB over CAI for optimum condition was cos alpha I by 2. So it means you get lesser CB, right? So now let's move on. Now we can calculate the optimum power corresponding to this point, or maximum power which we can get. So this is the equation which was derived for 50% reaction turbine, CB into delta CW, and this was delta CW to CAI cos alpha I minus CB. Okay, so now in this equation we can replace cos alpha I with CB over CAI for optimum condition. So after simplification, the maximum rate of doing work or maximum power output per unit mass flow rate, because here m dot is not written, so it means it's for 1 kilogram of fluid flow, and that is CB square, right? So, and in case of impulse turbine, this was 2 CB square, but in case of reaction turbine, it comes out to be CB square, right? But in case of reaction turbine, CB will be higher. For the same CAI, in case of impulse turbine, CB was less because CB over CI was cos alpha I by 2. But in case of reaction turbine, for the same CAI, CB is higher, so that's why there is no 2 here. So, but CB is significantly high because CB is equal to simply CAI cos alpha I for this optimum condition. Similarly, now we can find out what is this maximum possible diagram efficiency corresponding to this point when CB over CAI is equal to cos alpha I. So the maximum diagram efficiency in this equation 2.17, you will replace CB over CAI with cos alpha I corresponding to this optimum condition, and after simplification, this is the final form of maximum possible diagram efficiency in case of reaction turbine or 50% reaction turbine. In case of impulse turbine, if you remember, that maximum diagram efficiency was cos square alpha I, but in case of reaction turbine, it's more of a complex equation. And but note down that if alpha I is 0, then the maximum possible is still 1, just like in case of impulse turbine. It was simply cos square alpha I. So in case of impulse or in case of reaction turbine, for alpha is equal to 0, the maximum possible is of course again 1, right? But the situation will be different for different alphas other than 0, because we know alpha is not taken as 0. It is normally chosen around between 10 to 30 degree. So for other values of alpha I, the efficiencies, maximum possible efficiency for the case of impulse and reaction turbine will be different because this equation is different. But for alpha is equal to 0, the maximum possible is 1. Okay. So For reaction turbine, for maximum efficiency condition, we have now considered that CB over CAI will be equal to cos alpha I. CB over CAI is equal to cos alpha I, and for alpha is equal to 0, CB will be equal to CAI, because CB over CAI is equal to cos alpha I. For alpha is equal to 0, CB will be equal to CAI. But we know alpha is not 0, so for other values of alpha, CB will be a little smaller than CAI. For example, CB over CAI is equal to, let me write it here. So now we know CB over CAI is equal to cos alpha I, cos alpha I. So for alpha 0 means CB is equal to CAI. For alpha is equal to 10 degree or 15 degree or 20 degree, alpha is not more than 20. So then CB is nearly equal to CAI, a little smaller, but not exactly equal to CAI. So in this case, CB and CAI are very close to each other in case of 50% reaction turbine. So for this optimum operating conditions, your velocity diagram would look like this one for this optimum condition. And what you notice here is that it becomes exactly vertical, the CRI, because CAI is almost, sorry, CB is almost equal to CAI. If alpha is equal to 0, then CB will be exactly equal to CAI, but we know alpha is not equal to 0. And for other values of alpha, like 5 degree or 10 degree or 15 degree, CB will be nearly equal to CAI, a little smaller than CAI for this optimum condition. That's why the velocity triangle would look like this one, which you are seeing now. So for reaction turbine, for maximum efficiency condition, I'm again repeating that CB over CAI is equal to cos alpha, means CB is equal to CAI for alpha is equal to 0, or CB is a little smaller than CAI for alpha is equal to 10 to 20 degree. That's why under optimum operating conditions, optimum blade to speed ratio CAI over CB over CAI is equal to cos alpha I. The velocity diagram will look like this because CB is nearly equal to CAI, right? Okay, and this was the equation, the general equation of diagram efficiency, and I already explained in the previous slide. If you draw the curve between this diagram efficiency versus CB over CAI, you will get such a curve in case of reaction turbine, and here is the maximum, and this maximum is cos alpha I for reaction turbine. If on the same graph, if you draw the curve for impulse turbine, then the maximum was cos square alpha I, right? For alpha is equal to 0, both will have the same value, but here it is not for alpha is equal to 0, it is for any other value of alpha. These curves are shown, for example, alpha is equal to 10 or 15 degree. So you will see this value for maximum value in case of reaction turbine will be a little larger than the impulse turbine. The maximum value of efficiency in case of reaction turbine, it will occur at a higher value of CB over CAI compared to simple impulse turbine. It was at a lower value of CB over CAI, and also the maximum value is smaller than the maximum value in case of reaction turbine, right? So that's why based on this we can say that reaction turbines are more efficient compared to impulse turbine, right? Now we also notice that in case of reaction turbine, CB is higher value. Here you can see it is CB over CAI is equal to cos alpha. But now to keep CB lower, because we know we cannot have very large CB because of mechanical reasons of strength, then in case of reaction turbine, CAI should be kept lower. That's why reaction turbines are normally used in low pressure regions, so that CAI remains low, and the resulting value of CB should be lower too, because CAI is nearly equal to CB for a reaction turbine. So that's why for high pressure regions where you get very high value of CAI, it is usually the impulse turbine is used, because even for very high value of CAI, CB is quite less, corresponding to optimum condition, because optimum condition tells us that CAI over CB over CAI is equal to cos alpha I by 2. So that's why for high pressure regions, impulse turbine is preferred, and for low pressure regions, reaction turbine is normally preferred. So, and also we have discussed that maximum is not same. This maximum will be same if alpha is equal to 0. Both will have maximum of 1, but the maximum will occur at different points. But for any other value of alpha, always reaction turbine will give you higher efficiency than the corresponding impulse turbine. For example, for alpha is equal to 10, if you put value of alpha equal to 10 degree, maximum efficiency for the case of reaction turbine will be 0.985, around 0.98, and the maximum value for impulse turbine, it will be 0.97, a little larger, smaller than the corresponding reaction turbine. So for higher values of alpha, for example 15 or 20 or 30, this difference will be much larger. Reaction turbine will give you higher efficiency than the impulse turbine. So here, and another thing you can notice from this graph is that a variation in this cos alpha I and CB over CAI can be accepted without much variation in the diagram efficiency. It means for a larger value of, for a larger range of CB over CAI, the maximum efficiency remains near to 1, because here the curve is kind of flattened at the maximum point compared to impulse turbine. Here the curve is not flattened, here it is more like a sharp edged. So with the small change in the cos alpha I, in the CB over CAI, suddenly the velocity, efficiency will drop if you go in this direction or in this direction. A little small change in CB over CAI will drop the efficiency, while in the reaction turbine, a small change in CB over CAI will not drop the efficiency, because here the curve is more of a flat at the highest point. So that is one more thing which is noticed in case of reaction turbine compared to impulse turbine. Okay. So now here you see the compounding in case of reaction turbine. The purpose of compounding in reaction turbine is exactly same as in impulse turbine. And what was that reason? The reason is to reduce the blade speed CB to a reasonable safe value. So there were 3 different types of compounding in case of impulse turbine, but in case of reaction turbine there is just one type of compounding, and that is pressure compounding. As you see here, it is just fixed moving blades. So this is the compounding which in case of reaction turbine. So in reaction turbines, compounding is done similar to that in impulse turbine. The purpose is same, that is to reduce the speed of rotation of the shaft or the wheel. So here you see again, if it is not clear what is the axial direction and what is tangential direction, that is the axial direction in which steam is flowing, and that is the tangential direction in which the power is obtained. So here again you see pressure is dropping not only in the fixed blades but also in the moving blades. Fixed blades are nozzles, moving blades are also acting like nozzle, but those are movable. So the direction in which the blades are moving is also clear, because steam would be flowing like this from nozzle, and then in the moving blades, so steam is moving like this, so it will exert force in this direction. right? So pressure is continuously falling in all the blades, whether fixed or moving. And here you see the variation of velocity, absolute velocity. So absolute velocity increases in the fixed blades because fixed blades are fixed, they are not moving. The absolute velocity drops in the moving blades, absolute velocity, not relative velocity. And then again increases because again pressure drops in the fixed nozzle, so that's why absolute velocity increases and then again drops. So that's how the absolute velocity is keep on increasing, then decreasing, and again increase and then decreases, so on. So you may have a number of such rows of fixed and moving blades to increase the number of stages. So here one fixed and one moving makes one stage. So here on this screen you see a two-stage axial flow reaction turbine, two-stage axial flow reaction turbine. It could be 3-stage, 4-stage, 5-stage, depending upon the particular design of a steam power plant or the amount of power which needs to be extracted. So because as the amount of power extracted increases, CB increases, but to keep the CB at a reasonable value, you increase the number of stages. Right, so pressure falls continuously as the steam passes over the fixed and moving blades of each stage. It is usual to refer to two sets of blades as the stator. So these fixed row of blades can also be referred as stator blades, and the row of moving blades can also be stated as rotor blades. So pressure drop across the rotor produces an end thrust. Here you can see that pressure is continuously dropping, and in case of moving blades, the pressure drop from inlet till exit will produce an end thrust or axial thrust because pressure is dropping in the axial direction. In case of impulse turbines, there was no pressure drop in the moving blade, but there was a change in flow velocity from inlet to outlet. Flow velocity was the velocity in the axial direction. So in case of impulse turbine, that end thrust or axial thrust was due to the change in axial velocity of the fluid in the moving blades. But in case of a reaction turbine, the change in axial velocity is negligible. It is actually the change in pressure in the axial direction that causes this end thrust, right? So this end thrust in case of reaction turbines is actually a product of pressure difference, that pressure which is dropping in the direction of flow of the steam and the area of the annulus, because this pressure multiplied by the area of the annulus means area through which the fluid is flowing. So that is that ring area which we have discussed in the previous question which we have solved of reaction turbine. So it is that area multiplied by this pressure difference across the moving blade gives you the force in axial direction, and that is called end thrust. So this end thrust or axial thrust is actually linked to moving blades, not to fixed blade, because fixed blades are attached to the casing, not to the shaft. So in case of shaft design, you have to be very careful about this end thrust. So end thrust in case of reaction turbine is due to pressure difference, and in case of impulse turbine it was due to the difference in axial velocity or flow velocity. So for the 50% reaction turbine, the thrust due to the change in axial velocity is almost zero compared to the thrust which is produced due to the change in pressure. Okay, now we have studied that end thrust or axial thrust is produced due to the pressure difference in the reaction turbine. So total end thrust is also dependent upon the amount of mass which is flowing through the turbine in axial direction, and also we know that the amount of mass which is flowing in the axial direction will determine the height of the blades. Okay, so let me show you here. For example, we have axial flow reaction turbine, multi-stage axial flow reaction turbine. So there is nozzle, then there is moving blades. This is one stage. So second stage will consist of another row of nozzles and another row of moving blades. Then if you need another row, third row, so you can see here height is continuously increasing in the axial direction. Right. So here we have drawn as an example three row axial flow reaction turbine. Right, so all the moving blades are attached to the shaft and nozzles are attached to the casing. The important thing to note here, and this is that the velocity of the fluid is, or the mass rate of the fluid is in this direction. That is the axial direction. And you can see here the height is continuously increasing till here. Here you have maximum height. If this is a 3-stage compounded turbine, if this is 6-stage compounded turbine, for example, then you can imagine the height will be very high, because in case of reaction turbine, in this direction continuously pressure is dropping. This pressure of the fluid is continuously dropping in the direction of steam flow. And what is this direction? This direction is axial direction. And with the decrease in pressure, what is increasing? Specific volume. As the pressure is continuously dropping, specific volume would be continuously increasing, this specific volume. So when volume of the steam is continuously increasing, so you have to increase the height. This height of the blade has to be increased continuously so that steam can occupy a larger space, because pressure is continuous. Pressure needs to be dropped, because this drop in pressure is actually converting into work done. But with the drop in pressure, volume of the steam increases, and to compensate for this increased volume, the height of the blade has to be increased so that the annular flow area is increased. And because we want to keep this m dot v constant throughout, m dot into v should be constant throughout. So to keep this volume flow rate constant, and here volume is increasing, so you have to increase the height. Okay, so here you will see the end thrust in this direction will be huge, right? Because all of the mass is flowing in this particular direction. So end thrust on this shaft will be highest because of so many blades, or so many fixed and moving blades in one particular direction, right? So the end thrust is produced due to the pressure difference in case of reaction turbine. So total end thrust is also dependent upon the mass which is flowing m, right, flowing through the turbine in the axial direction, because this m dot multiplied by this pressure force will be a huge value as far as the end thrust is concerned. And also we know that the amount of mass flow in the axial direction will determine the blade height. Now to keep the end thrust or axial thrust small, and also to keep the height of the blade reasonably smaller, a method is used which is shown here. So let me omit all these. So here you see a method to keep the end thrust small and also to keep the height of the blades reasonably smaller. This method is used, as you see in this figure. Here all this mass of the steam entering into this reaction turbine, right, is admitted at the center of the compounded blading, and the flow is divided into two halves. Now the total m dot is divided into two halves, m1 and m2 equally, and that's why by this amount the steam is reduced. into two halves, and the axial thrust is divided into two halves also. And also the height of the blades will not be too high in both directions, because total m dot is divided into two parts, right? Compared to the previous scenario which we have seen before, that all of the fluid was flowing in one particular direction. But now in this case, all of the fluid is divided into two halves, so m dot is divided into two halves. So that's why blade height will needs not to be too high in both directions, because m here it is m dot 1, so blade height will be calculated on the basis of this m dot 1, and in this direction blade height will be calculated on this m dot 2, and that's why the blade height will not be too large, and also the end thrust is also divided into two halves, right? So in this way the end thrust is reduced, and also the height of the blades are not too large when the steam is admitted into the center and then divided into halves. So after leaving, the same steam is now combining, the same mass flow rate is combining here in the condenser. The total m dot, as far as the total, okay, let me show it here. So this was the other case in which all the fluid was flowing in one particular direction. So this has been all right. So net end thrust can be reduced by admitting the steam to the casing in the midsection and allowing it to expand outwards to each end of the casing, passing over equal sets of blades on both sides. Here is the explanation. So this has the additional feature of reducing the blade height at a given wheel for a given total mass flow rate. The total mass flow rate is same. Okay. Let me remove it. So now the total mass flow rate is same. If I draw a system boundary here, this is the mass flow rate m dot, which was coming from boiler, and it is leaving this system as again m dot, right? So this m dot was divided inside the system into two halves. It was m dot 1 and m dot 2. So for this system boundary, the same m dot is entering and the same m dot is leaving, right? And total enthalpy drop from this point h1 to this point h2. So the total power output is same because m dot is same. This m dot is divided inside the boundary into two halves, right? So the advantage was that now you can reduce the blade height and also you can reduce the end thrust on both sides. So this was the major advantage of reducing. So this kind of configuration has the advantage of reducing the blade height at a given wheel for a given mass flow rate. So here you see another pictorial view. Here you see a huge reaction turbine. So here it is divided into two halves. So the mass would be entering here at the center, and then it is divided into two halves. If all of the mass would have been entering from one point, then this blade height in one particular direction would have been very large, and the end thrust in one particular direction would have been very high. So, but using this configuration, you can reduce the end thrust. Okay, so now this was about the compounding of reaction turbine. Here you see a summary of all different types of compoundings which we have studied in this chapter of steam turbine. So here you can see this is a fixed nozzles and turbine blading, and the structure or the shape of the blade tells us that it is an impulse turbine or impulse turbine blades. Then another row of nozzles, another row of moving blades, and moving blades are impulse type, so that is a pressure compounding. Here fixed row of nozzles, then moving blades, fixed blades, moving blades. This was also impulse turbine but velocity compounding. Then here two velocity compounded turbines are attached in series with each other, then it becomes a pressure velocity compounding. So these were the three different ways of using compounding in case of impulse turbine. For reaction turbine, it is only just one way of compounding, and that is fixed blades, moving blades, fixed blades, and moving blades. So these are the different types of compoundings which are used in case of steam turbines. These three are for impulse type, and this one is for reaction turbine. Here you see a figure of a large steam power plant. The power plants which are used to produce power in megawatts, hundreds or thousands of megawatts. So in such power plants, the steam turbine is not just impulse turbine, or it is not just reaction turbine, it is a combination of both. Here you see a one long shaft, okay, and on this one single shaft there are three turbines are attached, and these three sections of steam turbine, they are high pressure section, then intermediate pressure, and low pressure section or turbine. So all three of them are mounted on the same shaft, which rotates at around 3600 rpm in a generator to make electricity. So here is a simplified steam flow path through this high pressure, intermediate or medium pressure, and low pressure turbines are shown. So here we shall I will only explain the turbine section. For the time being, just forget about condenser and feed water heaters and boilers. That is something which you will learn in coming chapters or in the course of power plants. So here our focus is only on the turbine section. So here is the main steam, or steam coming from the boiler at about maximum temperature. It could be around 550 degrees Celsius, and pressure could be in the range of 150 bars. And now it goes to the high pressure turbine, and this high pressure turbine is normally an impulse turbine. So it is a impulse compounded turbine. So main stream goes over this multi-stage blades and expands, reducing the temperature as it leaves this high pressure turbine. The turbine size is the smallest at the inlet of this steam, and because the pressure is very high, and because of very high pressure, the volume is quite low, right? So although steam is expanding, but because of very high pressure, the volume is not very high. So that's why the blade height is increasing, but very slightly, only due to drop in velocity, but not due to drop in pressure. So steam, when it leaves this high pressure turbine, now it enters into the next intermediate pressure. But before it enters into the intermediate pressure, this steam is sent back to the boiler to again reheat to about temperature 550 degrees Celsius, but pressure is now dropped to about 30 bars. It was about 150 bars to about 30 bars when it's an impulse turbine stage. So all of the pressure is normally dropped only in the nozzle section, right? So now this steam is now brought into the intermediate pressure turbine. So its path to the boiler is not shown here. So we'll not be discussing this thing. It will be discussed in the next chapter, in the chapter of steam power plant. So here the steam leaving the high pressure turbine goes back to the boiler, where its temperature is again increased to 550 degrees Celsius, but pressure is not increased. So this steam now enters into a intermediate pressure, or the medium pressure section, right? So here the pressure has already been dropped, volume is increased, so that's why you see here bigger piping, and a larger turbine is required to handle this steam flow. So this medium pressure section of the turbine is bigger than the high pressure turbine for this reason, because volume is now increased. So this medium pressure turbine outlet is now connected with one, or it could be more than one So one or two low pressure turbines rotated. So low pressure turbine further expands the steam, as we have discussed. Here it is entering at the center and then it is divided into two halves. And low pressure turbine further expands the steam, generating more power on the same shaft. All these sections, high pressure, low pressure and medium pressure, are attached to the same shaft. So low pressures are the biggest in size, since they have the lowest steam pressure here. Hence they require bigger area or larger area to handle the same steam flow rate, right? So this is so here you see the steam is divided into two halves, and here it is collected, or it will be sent to the condenser as one steam later on. Okay, so with this, the compounding of the steam turbine is almost finished. So we'll come back in the next video with the next topic.